And welcome to organic functional groups. What are the organic functional groups? These are a specific arrangement of atoms in an organic compound that have specific chemical properties. Who cares? These molecules have hydrocarbon stems in them, which we've already studied, but because of the presence of different elements, they act differently than regular hydrocarbons. You don't need to really fully write these definitions out, but what's important to understand is that these molecules are not hydrocarbons. They have other elements in them, and therefore they're going to have different properties than the hydrocarbons. What do you need to know? Yeah, I would not write all of this stuff out, but what I really want you to understand is that you do need to know a lot about these molecules. You need to be able to identify them. You need to be able to draw or name them, and you need to be able to understand that they have isomers. You will have table R to help you with this, and you want to get very good at depending on table R. Otherwise, you're going to be doing a lot of memorization. Table R is a very large table. You want to make sure that you have it open while you are following along with these notes. First class of compounds listed on table R are what are called the halides. The halide functional group, which we see in this column right here, is a group 17 element. Over in our last column where we have an example, we can see that there's a Cl, or a chlorine atom, in this otherwise carbon chain. This R right here means that we're talking about a carbon chain, and in this case, this means we have a carbon chain with a halogen somewhere bonded on it. So our functional group is going to be a group 17 element. Our general formula is that Rx, meaning we have that carbon chain with that halogen bonded to it. These are very similar to the alkanes, but will be different because of that group 17 element. They really stand out among the other different compounds we're going to be talking about. Using your example, you need to be able to name these. What you'll notice from this example is that there's 1, 2, 3 carbons. This molecule is actually 1, 2, 3 carbons in a row, and off the middle carbon is a chlorine. Now that you can see this drawn out, you can really see that there's a propane chain to it. We're just using our table P prefix prop, meaning 3. So when you name these, you're going to start by having basic alkane naming. Then you're going to use, your ending will not change, then you're going to use a halide, or halogen, I should say, prefix, which are given again right here. So that prefix is going to be the name of your halogen. Your suffix will just be your alkane ending. You can also have halides bonded to other molecules that are not alkanes, but we will strictly be talking about haloalkanes. And you do need a number to tell where halogen is bonded. So in our sample molecule, you see that if we number this guy number 2, that's where our chlorine atom is. Some examples of halides, one that was very important in the news for a long time, are refrigerants from the CFCs. CFCs were very important because they actually broke down the ozone layer. The sun's UV rays break these molecules down. They can actually break this chlorine right off, causing a chlorine-free radical, which depletes the ozone layer. Haloethane is an anesthetic. And freon, again, is just another group of compounds such as the ones mentioned above. Halocarbons are rarely found in nature, easily produced in labs. They have weak intermolecular forces and are usually gases at room temperature. The fact that haloalkanes are gases at room temperature is why they were able to be used as refrigerants and how they got into the atmosphere in the first place. What you can notice from this table, if you compare methane to some haloalkanes, the halogen atom actually does affect the boiling point. As you'll notice, you get much larger GFMs once you start replacing hydrogens with group 17 atoms, and this will drastically increase your boiling point. Next, we have the alcohols. I'm going to go through these somewhat quickly because we will study the alcohols in a little bit more detail in a different video. Alcohols have a hydroxy functional group. It looks like an OH, kind of like what's in the base. What is in a base? Only the difference is that it has to be attached to a carbon-based chain. Alcohols are carbon-based. We don't have the OH attached to a metal. Similar compounds to these, again, are the bases, but we're not going to mention them here because they're not organic. Ethers are the most similar compounds to these that we're going to talk about today. You should look for one O in an OH group that usually sticks off the molecule, and we should have a carbon chain. You can have, I'm actually going to take off the one O because you can have more than one O. We can have something called a di or trihydroxyalcohol, which we will talk about separately. As we're looking at naming these, if you look at your example of 1-propanol that is given, prop, as you remember, means 3. And you can count that there are 3 carbons in that molecule. If you were to draw this out, you'd have 3 carbons with an OH on the end carbon. So the prop is talking about those 3 carbons. This one right here is talking about the fact that this is on end carbon, or carbon number 1. You could draw that OH on the other side of the molecule. It just tends to be drawn on the end. So when we name these, we're going to name the alkane. We're going to change the ending to OL, and we're going to put a number for the OHs. Our prefix is just our typical table P prefix, telling us the number of carbons in the molecule. Our suffix is our OL ending, and yes, we do have a number telling where that OH alcohol group exists. Again, we're going to discuss these more in detail at a later time, but a lot of examples of alcohols are all around us. You've definitely heard of ethanol. You learn about that in health class, which is what we call, booze, drinking booze, if you will. Also used in things like mouthwash and other consumer products. Methanol is poisonous alcohol. This is actually just a 1-carbon alcohol. A very little amount can cause blindness, and a pretty significantly small amount can actually cause death. And then 1,2,3-propane triol, which we'll actually look at in notes on a separate day, is known as glycerol, and it's found in soaps and similar types of products. The ethers are fairly similar. Ethers are actually molecules that have just a single bonded O right in the middle of their carbon strands. So this is one group that can have any number of carbons in it, and this is another group that actually can have either the same or a different number of carbon atoms in it. These are most similar to the alcohols and can be identified by the product by looking for a 1O in the middle of the molecule. We'll draw one of these out to take a look at it. Well, we want to name an ether. So if we look at our example from table R, our example in table R is something called methyl ethyl ether. I like to identify that ether functional group right there. What this really looks like is CH3, O, CH2, CH3. As you can see, you have a 1-carbon group over here that when we named the alkanes, we called this substituent a methyl group. Over here, we have a 2-carbon group that we would have called an ethyl group. So we're going to call this methyl ethyl ether. We put the methyl first simply because there's fewer carbons in it. So that just tends to be how this is done. So for our naming, we're going to name each branch or substituent. And then we're going to put the name ether on the end of this. So our prefix will be our substituent. Our suffix will be ether. Oops, sorry. use numbers because our naming of our substituents actually tells us how many carbons are on each side. Our methyl group has 1 carbon. Our ethyl group has 2 carbons. And then they're simply strung together by that oxygen. Another important molecule is something called dimethyl ether. In dimethyl ether, I would start by saying, hey, I gotta have an O in the middle. Then I have 2 methyl groups. 1 methyl group here, 1 methyl group here. You could also have dimethyl ether, and you can even have propyl ethers. Diethyl ether, which would be an O in the middle and an ethyl group on each side, was the first reliable general anesthetic that reported in the late 1800s. This was a huge change in medicine, the ability to do surgeries without patients going into shock, and a big change in how we practice medicine even today. You can kind of get that image of a cloth being soaked in ether and being put in front of a patient's face to knock them out for a particular procedure. Aldehydes and ketones are next. The aldehydes have a carbon with a double bonded oxygen. You're also going to notice that there's just this hydrogen right here. This functional group has to come on the end of the molecule. That is extremely important. So my aldehyde functional group is this end carbon with an O and an H on it. They show that H bonded, but really it's just stuck to that carbon like any other hydrogen would be. So we're going to have a carbon chain, and you could even just show it in your little shorthand like that, and that double bonded O on the end of the molecule. These are similar to the ketones. To identify these molecules, look for 1 double bonded oxygen. No other oxygens, just 1. And look for that to fall at the end of the carbon chain, or on the end of the molecule. Ketones are going to be different because we're going to have that double bonded O still, but it's going to be in a different place. When we want to name our aldehydes, these are among some of the easiest to name. Simply count how many carbons are in your chain. 1, 2, 3. Make sure to include the carbon of the functional group. 3 carbons give us that prop prefix. So we're going to start by calling this propane, for example. So we start by alkane naming. And then we're going to, instead of calling this propane, we drop the E on the end of propane, and we change it to an AL ending. So propane becomes propanal. We're just using a simple table P prefix. Our suffix is that AL ending. And we don't need any numbers because the group is always on the end. So technically it would always be 1 whatever. Since that's a given, we don't want to have to write excess numbers. I apologize, I lost my recorder box and got a little bit nervous. Our next functional group are the ketones, which are similar because of that double bonded O. The difference is this time, we see those R's in our general formula. What the R's actually mean is that we can have different number of carbons on either side. So we're going to have a carbon chain here, and we're going to have a carbon chain here. They may be the same number of carbons in each one, they may be completely different. These are most similar to the aldehydes. And we identify them by looking for 1 double bonded oxygen in the middle of the molecule. When we're going to name ketones, if we simply look at our example down here, these are fairly straightforward to name as well. If we were to number these carbons, 1, 2, 3, 4, 5, that goes along with my prefix that I see right here, pent. Number 2 right here is indicative of where I've attached my my oxygen double bond. So I'm going to first name the alkane chain. I'm going to second change my ending. Instead of calling this pentane, I would drop my E and call this pentanone. And then I'm going to give a number where I have my double bonded oxygen attached. So my prefix will be from table P. My suffix will be -one. And yes, I have numbers to tell where my double bonded oxygen is. There is a slight exception to the rule with the double bonded oxygen and the number. If you had this molecule right here, this is absolutely a ketone because we have a double bonded O in the middle of the molecule. 3 carbons in a row would make this propane or propanone. Because the double bonded O has to be in the middle of the molecule, there's no such thing as 1 or 3 propanone. That would actually make this an aldehyde. So this has to be 2-propanone. Because it has to be 2-propanone, you can actually get away without giving this guy a number. Property or comparison between the aldehydes and the ketones is that they both have 1 double bonded oxygen. The difference is in the aldehydes, this has to be on the end of the molecule, and in the ketones, it cannot be on an end carbon. It doesn't have to be directly in the middle in terms of the exact same number of carbons on either side, but it has to be on a carbon that is not the end of the molecule. Properties of these molecules, they're generally small molecules that are pretty water soluble. They tend to be pretty polar because they're pretty asymmetric, especially the aldehydes. The intermolecular forces are somewhere between the hydrocarbons and alcohols, so they have pretty moderate boiling points. You will tend to be able to smell them a lot because they do vaporize a little bit more easily than something like water. They're also often isolated from plants, and many of them produce strong odors. Some examples of a couple aldehydes: cinnamaldehyde smells like cinnamon, and benzaldehyde, which is extracted from almonds, smells like almonds. Methanal is also known as formaldehyde, which is used to preserve dead bodies. And propanone, which is a ketone that I drew a couple minutes ago, is also known to you as acetone. So if you've handled acetone as nail polish remover or as for something else, you have handled a ketone.